Sure. Do you guys have any question from the last lecture? Let's get this sorted. Is the screen visible properly?
Yes, sir.
Yes, sir.
Okay, good. So we'll get started with wherever we left in the last lecture. Essentially, what we are looking at is the transport of heat across the planet. And why is that necessary? A quick recap. Whatever wind and water mass movement that we observe on the surface of the planet is to account for unequal distribution of heat across the globe. And what this circulation is trying to do is to bring the planet into a thermal equilibrium. Okay? And what we know about the controllers of global temperature, the first aspect is the incoming solar radiation, which is modulated by the planet's orbital motion around the sun. And the second aspect is the amount of greenhouse gas in the atmosphere. And these are very two important aspects. For the rest few lectures, we're going to focus on the greenhouse gases because global warming, as we know, is an important phenomenon. Um, who is this? Could you please mute yourself, everybody? Hang on, let me check. Okay, better. Okay, please ensure that you have muted yourself. Okay, otherwise I get a bit distracted and it's very difficult for me to follow up. Okay, so we're going to focus on the greenhouse gases for the few lectures to understand how their concentrations have changed and what's the implication of it. But for now, what we are focusing on is the role of ocean circulation and wind circulation in terms of changing the global temperature or redistribution of heat across the planet. Okay. Now, quick recap. We have two major heat sources. One is the sun, which is bringing in around 180,000 terawatts of energy per year. And then there is the internal heat, which is around 43 terawatts. This 43 terawatt is responsible for the mantle convection, which leads to the movement of plates, as we know, collectively known as plate tectonics, and all the volcanic activity and other stuff that we observe on the surface of the planet, which has some heat coming from the interior, is driven by this 43 terawatt. But the maximum or the lion's share is the 180,000 terawatts that we receive. And most of it is modulated by the Earth's orbital motion around the sun. One is the change in its eccentricity or the shape of the orbit. The other one is the axial precession, or known as wobble. And then there's the change in obliquity, the tilt. Okay. And the greenhouse gases are absorbing the back radiation and thereby heating up the planet. The key greenhouse gas that we are interested in is in CO2. The vibrational modes of CO2, which leads to a change in its dipole moment, are dominantly IR active. So they are absorbing the infrared zone back radiation of the planet and leading to global warming. Just to summarize what we did in last lecture, in terms of energy received, we have the solar constant times the surface area across which we are receiving the energy. And 1 minus A stands for the albedo effect, where A is the albedo effect. For planet Earth, we take an albedo of 0.3. Albedo is nothing but the reflectivity of a surface, how much incoming radiation is absorbed and how much is reflected back. For a perfect black body, the albedo will be close to 0. And for a perfect white body or perfect reflective surface, the albedo will be close to 1. And this is the back radiation that we observe. and where TE is the temperature of the planet in thermal equilibrium with the incoming solar radiation. A quick calculation gives us a value of Earth's temperature should be minus 18 degrees Celsius based on what sort of solar energy we receive. However, the observed temperature is 15 degrees Celsius, and this is caused by the CO2 absorbance of infrared back radiation. Now, this is the key picture. This is the energy balance of the planet. What we have is on the x-axis, latitude going from 90 degrees north to the left to 90 degrees south to the right. And then there is the radiation intensity in joules on the y-axis. The red line is your shortwave solar radiation that we are receiving. And this shape is typical, integrated over seasons. And what we can see at the equator, we receive the maximum amount of solar radiation. And as we move towards the pole, we receive less and less solar radiation. The green line is giving you the back radiation from the Earth. If Earth were a perfect black body, this green line would be a straight line. However, what we observe that the green line has got a polar dip versus an equatorial rise because the surface temperatures are different at different regions. But what is the key is the net energy excess between 35 degrees north and 35 degrees south, whereas the energy deficit between 35 degrees north and the poles. So heat or energy from this area of the planet has to move towards the deficit area of the planet, and that is what is driving the air circulation cell, as we discussed in an ideal planet which is not rotating. However, since the planet is rotating, this is what we get. The circulation cell is broken up into multiple cells, the Hadley cell, the Ferrel cell, and the polar cell, right? And the direction of the wind movement is dominantly controlled by the Coriolis effect. What is Coriolis effect? Coriolis effect is the pseudo force that's applied on anything that's moving along the surface of the planet due to the rotational speed of the planet. At the equator, you are rotating at the maximum speed, and as you move towards the pole, that speed is going to decrease. And conservation of momentum dictates that there is a deflection to the right in the northern hemisphere and a deflection towards the left in the southern hemisphere as you move from the equator towards the pole. Keep in mind, northern hemisphere to the right, southern hemisphere to the left during the movement from the equator towards the pole. Perfect. Now, in terms of circulation, we have two different types of ocean circulation. First one is the wind-driven circulation that happens at the surface. And the second one is the density-driven circulation that happens in the deep. Our focus is dominantly going to be in the density-driven circulation because that is something that's happening into the interior of the planet and is controlling a lot of the ocean chemistry, global climate, and everything. Okay. Now, before we move into the density-driven circulation, we're going to cover a very important aspect of wind-driven circulation, something that has a very strong impact on global temperatures, global climate, the amount of hurricanes you can observe in Pacific Ocean versus in Atlantic Ocean. Remember one thing, hurricanes or storms are just means of transferring energy from the equator to the higher latitudes. So as the globe warms up, the intensity and the frequency of these hurricanes and storms have to go up. Okay? So moving there, the first aspect of surface circulation is movement of water mass along wind circulation paths. What we can see is along the eastern boundary of every ocean, there is a movement of water mass from the north towards the equator. And in the southern hemisphere, it's coming from the poles towards the equator. So along the eastern boundary of every ocean, there is a net movement of water along the surface from the poles towards the equator. To compensate for that, along the western boundary, there is a movement from the equator towards the pole. Okay. And this is where Ekman spiral becomes important. I think you guys have done a kind of an homework on Ekman spiral. Just to summarize, the net transport of water is usually or is definitely at the perpendicular direction to the movement of the wind. So Ekman transport dictates that if wind is moving from north to south, in the northern hemisphere, if I have a wind coming from north to south in the um, northern hemisphere, the movement of water has to be perpendicular to that direction. If the wind is coming in this direction, the water must move in this direction. Okay, perfect. Now, this phenomenon of Ekman transport leads to something what we call as upwelling. What is upwelling? Upwelling is when we have wind blowing along shore, like parallel to the shoreline in the northern hemisphere, coming from north to south. We know that the deflection will be to the right of the wind. That means the water mass will start moving away from the shoreline. And we also know that the water has to maintain the same level. To maintain the same level, and if I keep transporting water from the shoreline towards the open ocean, there has to be transport of water from the deep ocean to the open surface ocean. And this is known as upwelling. This only happens when there is a longshore wind movement from north to south in the in the northern hemisphere, and it's dominantly happening along places where you have this sort of ocean to continent boundaries, and an eastern boundary of an ocean or a western boundary of a continent. The red marks are the upwelling zones, are dominant hotspots of this sort of upwelling. Now, please keep in mind that upwelling can be a seasonal phenomenon in the higher latitude. Why am I saying this? This is for a simple fact. Let's go back to this diagram. These are my circulation cells, like the polar cell in the northern hemisphere is extending up to 60 degrees north during, I would say, during summer. But as winter progresses, the polar cell is going to encroach further southwards. Keep in mind, when the polar cell is active, the movement of air mass from the northernmost point to the southernmost point of the cell is along a north-south direction. Now, if there is a north-south direction of airflow, the water will be deflected to the right, and so we will have upwelling along the coast of North America over this region. However, if this polar cell keeps extending southwards, the upwelling zone is going to extend southwards. So during summer, this part of North America will not be an upwelling zone because this part of North America is under the feral circulation cell, where the air mass is moving from south to north, and along this western boundary, the water mass has to be pushed towards the boundary. So there is no net movement of water away from the continental margin. So we can safely say that during summer months, this boundary is not an upwelling boundary. However, during winter months, as the polar cell progresses southwards, the wind direction changes and there is net water movement away from the continental boundary. So when we look at a picture like this, which gives you a overview of where upwelling happens in the ocean, this is not telling you whether the upwelling is a seasonal upwelling or whether the upwelling is a constant year-long upwelling. Usually along the equatorial region, there is not much change in wind direction. So any upwelling you observe along the equatorial region has to be a, a yearly kind of phenomenon. However, the intensity of the upwelling can change with season as the wind speed changes. But usually at high latitudes, when you see upwelling, that upwelling will be a seasonal phenomenon because mostly the wind direction will change strongly with seasons. Now, when we try and measure the extent of upwelling, what we do is we look at the chlorophyll concentration of the surface ocean because upwelling usually brings deep water from the bottom of the ocean to the surface, and those deep waters are usually rich in nutrients due to bacterial activity. Now, one of the major most upwelling phenomena that controls global climate, which includes temperature, the mean annual temperature of the planet to mean annual precipitation of the planet, is the event known as El Nino. Now, sometimes when there is drought in India, people say this is an El Nino year. Sometimes there is a lot of rainfall in India, people say it's a La Nina year. So what is the connection between El Nino and rainfall, La Nina and rainfall? Let's try and understand that. This phenomenon happens in the equatorial Pacific Ocean. And the question will become, why would a phenomenon in equatorial Pacific Ocean be so important for the globe? From the perspective of the planet, equatorial Pacific Ocean covers almost 50% of the equatorial aspect of the planet. So the amount of heat received in equatorial Pacific is 50% of the peak heat that the planet, or the peak incoming solar radiation that the planet receives. So any change in the equatorial Pacific dynamics has a huge impact on the surface temperature of the planet. Now, under normal years, the equatorial Pacific has a circulation cell, hang on a second, which looks like this. In a normal circumstances, air mass movement happens in this direction, which takes the water along with it in the equator, and thus leading to an upwelling, which means that there is a formation of warm pool in the western equatorial Pacific. This is the western equatorial Pacific, this is the eastern equatorial Pacific. If there is a net water mass movement from eastern equatorial Pacific to western equatorial Pacific, there will be upwelling in the eastern equatorial Pacific and formation or the pooling of the warm water along the equator in the western equatorial Pacific. This is a normal scenario. An El Nino year is the year when this wind circulation pattern slows down. If the wind circulation slows down or reverses in direction, then there is no net air movement from the eastern equatorial to the western equatorial Pacific. If there is no net air movement, then there is no upwelling in eastern equatorial Pacific. So the warm pool that we observed in the western equatorial Pacific in a normal condition starts spreading eastward towards the South America, the Chilean margin, and we have this large warm pool in the entire equatorial Pacific. And that is kind of given in this picture. This is the snapshot of an El Nino year. What we are looking at is a temperature anomaly. This is not real temperature, this is temperature anomaly. The blue color are the cooler colors, ranging from -4 degrees Celsius to +4 degrees Celsius in the red colors. This is your deviation from your mean average, say over the last 25 years or 50 years. Okay. So if a particular year is warmer than the previous year, you means you have an anomaly, a warming anomaly. If it's cooler, you have a cooler anomaly. So during the El Nino year, we can see that along the eastern equatorial Pacific, there is a large warming anomaly. So places close to the Chilean margin gets really, really warm, up to 4 degrees Celsius warmer. And how do we explain that? Lack of transport of water from eastern equatorial Pacific to the western equatorial Pacific leads to a lower level of upwelling, and you can see that's denoted in the thermocline. Thermocline is the depth horizon of temperature change as we go down in seawater depth. So you can see that in a normal year, the thermocline is shallow, so it's closer to the surface. And during an El Nino year, the thermocline is deep, right? So in terms of circulation pattern, this is what we observe. In a neutral condition or a normal cell, you have equatorial transport of air mass that forms a warm pool in the western equatorial Pacific, and this becomes a source of moisture almost for the globe. And there is also this source of moisture in the Atlantic Ocean. In an El Nino year, this warm pool spreads across the entire equatorial Pacific. You have a large amount of moisture formation in the eastern equatorial Pacific as compared to the western equatorial Pacific. Any question? Now,
Excuse me,
this
sir.
is, yes, go ahead.
So just to confirm, you're
Yeah.
calling the region near the North America the Eastern Equatorial Pacific, right?
Yeah, this is the eastern equatorial Pacific.
Okay.
This is the western boundary of North and South America, but the eastern boundary of the ocean, right?
Yeah, got it.
Okay.
Thank you.
So this is the difference between El Nino and a neutral condition, And then comes the event known as La Nina, where the wind speed, the size of this arrow gives you a measure of the wind speed. During neutral condition, you have some amount of air movement along the equatorial Pacific from the east to the west. During El Nino, it is reversed. The air circulation pattern has reversed, so you're essentially pushing the water towards the eastern equatorial Pacific. Whereas during La Nina, this normal circulation cell is intensified. So the warm pool is pushed into the western equatorial Pacific, and that can spill over from the western equatorial Pacific into the Indian Ocean through the Straits of Malaysia and Burma. So there can be a net warming of Bay of Bengal if there is a strong La Nina event where the warm water mass is pushed towards the western equatorial Pacific. Okay. Now, how does these phenomena impact global climate? Okay. The first thing to look at is a difference in average temperature between an El Nino and La Nina event. And again, we are looking at uh, here, this is a scale in Fahrenheit because unfortunately this is done mostly by NOAA and NASA, and they still use the Fahrenheit scale. We are looking at a temperature difference of -9 degree Fahrenheit to +9 degree Fahrenheit. Please keep in mind, this is not an absolute temperature of -9 degree Fahrenheit and +9 degree Fahrenheit. We're looking at a temperature difference from a normal condition. Okay. So during a La Nina event, you can see that the equatorial Pacific is blue in color, which means it's cooler than what it should be. The cooler property comes from the upwelling of the deep water. And why is the deep water cooler than the surface water? We're going to come to that. But the basic idea is the surface water is being warmed up by the sun, and the deep water, when it formed, had already lost a lot of its heat from in the polar region. And we're going to cover that in details. Whereas in an El Nino event, such upwelling intensity diminishes, and we have formation of large warm pools in the eastern equatorial Pacific close to the continents. What is the impact of an El Nino? During a typical El Nino event, the equatorial Pacific is warm and wet because there is less upwelling. There is more hurricanes in the Pacific part hitting California, and there are fewer hurricanes in the Atlantic part hitting Cuba and Florida. Whereas during a La Nina event, there, the Pacific is cool and dry because there is not much warm pool, and as we know, higher the temperature, more the evaporation, more the cloud formation. And if I keep bringing up cold water from the abyss, I'm going to have a lower temperature of the surface ocean, less amount of cloud formation, less temperature gradient between the equator and the pole. So there will be less requirement of heat transport from the equator to the pole. Okay. So thus there will be fewer hurricanes because, as we had discussed, hurricanes are a way of dissipating energy or transferring energy from the equator to the poles. However, in the Atlantic Ocean, we observe the other way around. There are more hurricanes because, after all, the planet is receiving a set amount of solar energy per year. If Pacific Ocean is not transporting that energy from the equator to the poles, some other ocean needs to transport that energy from the equator to the poles, and the responsibility comes to Atlantic Ocean because Indian Ocean doesn't have access to the pole. Indian Ocean goes as far north as India is. Okay, so please keep that in mind. Now, this brings us to the deep ocean circulation. Before I start that, is there any question about El Nino La Nina? Okay, I shall move on. The deep ocean circulation is the bit that happens without us observing it day to day. A surface ocean circulation is manifested in ocean current, uh, like some places getting a warm current, some places getting a cool current. However, the deep ocean circulation is essentially the movement of water mass along the abyssal plane of the ocean. And the blue bit in this particular diagram gives you the cold water mass that sinks at the North Atlantic and all around the Antarctica. The North Atlantic water follows the contour of the ocean, travels from North Atlantic to South Atlantic, is then recharged by Antarctic bottom mass, and then it flows into the Indian Ocean where it's upwelled, and then it follows along the Southern Ocean into the Pacific Ocean, from South Pacific to North Pacific, and upwelled in North Pacific. And from North Pacific, the surface water has to make its way through the Indian Ocean, back to South Atlantic, all the way up to North Atlantic. So this is known as the Great Conveyor Belt. Wally Broker first proposed that, and based on seawater chemistry data, and we're going to cover that, that this is how water is being transported from the poles towards the equator along the abyss. And how much water is flowing? Now, let's put it in context. Amazon River has a flow of around 0.2 million meter cube per second. Okay, it carries almost 10% of all the surface water that there is. So if you take a global river average, Amazon River by itself has a 10% of all the freshwater river flux in the world. And that's equal to around 0.2 million meter cube per second. This water movement is 80 times the volume of Amazon River movement. So it's much larger than what we expect from entire freshwater flux across the globe. Now, why is this happening? The simple idea is, as the water moves towards the pole, it's losing its heat to the atmosphere. It's becoming cooler and cooler. As it becomes cooler, it becomes denser and it sinks. And once it sinks, it cannot exchange heat with the atmosphere anymore, or neither can it change its amount of salt in it. So it stays dense and it follows along the contour of the ocean bottom. Okay, so there are two aspects to this. First is, how do you change the density of a water mass? The density of a water mass can be changed simply by changing its temperature. Lowering the temperature will increase its density, or by changing the amount of salt content in the water. Adding more salt will make it more denser. So before we go into the details of how temperature and salinity, that is the salt content of seawater, affects its density, we're going to do a quick review of water as a polar protic solvent. We all know that water is a polar molecule, is a dipole moment, and readily forms hydrogen bond. Whereas keep in mind, ice has a tetrahedral structure, and there is no space for dissolved ions in an ice lattice, or there is very limited space for dissolved ions in an ice lattice, right? Now, this dipole moment has a huge impact on solubility of ions in water, right? The electron cloud depiction of water molecule is given on the left-hand side, and the structure of the essentially the hydrogen bonding between two water molecules is given on the right-hand side. I'm not going to go into the details of it because I'm sure this has been taught in excruciating details to you in your other chemistry lectures. But the physical properties of water that we are interested in as oceanographers are the following. First of all, it has a high melting point for the ice, okay, because we are looking at a salt solution. The maximum density of a normal water-based water ice system has the following properties: high boiling point, high melting point, high specific heat, high heat of melting, a maximum density of 4 degrees Celsius for pure water, okay, high surface tension, viscosity, and all that things. Now, this is manifested in this particular diagram very clearly. What we are looking at is looking at the boiling point of the group 16, like hydrides of the group 16 elements, starting from oxygen, sulfur, selenium, and tellurium. And what you look on the x-axis, we have the molecular mass in grams per mole, and on the y-axis, we have boiling point. Ideally, the tellurium hydride should have the highest boiling point, which is close to 0 degrees Celsius. So water should have a boiling point of around minus 62 degrees Celsius based on a simple molecular mass to boiling point relationship. However, water has a boiling point of 100 degrees Celsius. We are all aware of that. And this is dominantly because of the hydrogen bonding. And that hydrogen bonding allows for a lot of salt to be dissolved in seawater. Now, this is a table that gives you the major constituents of seawater. If anything, I want you to remember the top 6 or top 9 major dissolved ions of seawater. Why? You never know when it will come handy. Okay. The most abundant ion in seawater is chlorine. The most abundant cation in seawater is sodium. Then comes magnesium, then comes potassium, then comes calcium. Strontium is a minor cation in seawater. Among the anions, I have chlorine, sulfate, bicarbonate, carbonate, bromide. So keep in mind, these are the major constituents of seawaters. Some are singly charged, some are doubly charged. Okay. Now, most of these ions are hydrated. What do I mean by that? So they have a water of hydration around them, and they are surrounded by these water molecules. So they are not forming as salt and precipitating out. So seawater is oversaturated with respect to most salts that you can imagine forming out of seawater. However, this salt addition is causing electrostriction, which is essentially a shrinking in volume of the solvent as you add more and more solute. And it's true for a polar protic environment, and you have a polar salt added to a polar protic solvent. It's going to rearrange itself, so its volume is going to keep going down and down. On the left hand top side, we have the graph, which gives you the electrostriction effect for different kinds of salts, starting from magnesium sulfate, magnesium chloride, sodium chloride, and glucose, which is a non-ionic salt in this case. And we can use the volume density relationship from this chart and calculate that what happens when you add, say, around 30, this is, I think, applicable for 30 grams of dry anhydrous salt added to 970 grams of water. So their total volume should be a summation of the volume of the water plus the volume of the salt that you have added. However, that's never the case. There is always a decrease in the total volume, which leads to a change in the density of the system, because the weight of the system is not changing, because you're adding 970 grams of water plus 30 grams of salt. But the volume change will lead to a change in density. So remember, as the major ion composition of seawater can change, if the magnesium composition and the sulfate composition changes, the electrostriction effect will come into play. Now, do remember that there is no place for salt in ice. So whenever we have ice formation, the salt has to be extruded out. It's known as an effect called salting out, and the ice formed out of seawater is pure ice. It has no salt in it. With that idea, let's understand what is salinity. Salinity is essentially the amount of salt dissolved in seawater. You may say that I can take a liter of seawater, weigh how much it weighs, and then I can evaporate, collect the water that's coming out, weigh the amount of water that I received, and the amount of salt that was left behind. So I can calculate the amount of salt which is dissolved in a given volume of water. So I can easily get to my salinity. However, that's not the case. Usually salts like sodium chloride, potassium sulfate precipitates out of seawater very easily. Then comes the complex salts, which has a water of hydration. Okay. Magnesium chloride, calcium chloride, they are all associated with water of hydration. We have precipitation of magnesium carbonate, calcium bicarbonate. And if you keep driving the temperature up to get rid of the water of hydration, what happens is that the magnesium carbonate dissociates as magnesium oxide and CO2. And CO2 escapes as a volatile gas. So it is not possible to simply evaporate a parcel of seawater and get to its salinity. So over the time, scientists have tried to define what is salinity through multiple different ways. It started with the first definition that Kunsen gave in 1902 as the weight in grams of dissolved inorganic matter in a kilogram of seawater. after all the bromide and iodide have been replaced by equivalent amount of chloride and all carbonate has been converted to oxide, which is essentially his inability to drive away the last bit of water of hydration, and in the process of doing so, he is breaking down his carbonate compounds into oxide and CO2, and the CO2 has been lost. So for a long time, this debate raged. Then came the ideal definition for chlorinity. Now, what is chlorinity? Chlorinity is the unit is given in per mil. Per mil is nothing but percentage. Instead of dividing by 100, you divide by 1,000. Okay, so the amount of silver that you require to titrate seawater for its all chlorine, bromine, fluorine, iodine atom, right? So that is the definition of chlorinity. And from the definition of chlorinity, we can get to the definition of salinity, where salinity has a stoichiometric relationship with chlorinity, where salinity equals to 1.80655 times chlorinity. So this definition stood till the 1960s, 1970s. Beyond 1970s, this was a kind of a strange definition. We moved on to the practical salinity unit, okay, or known as the PSU. PSU is nothing but electrical conductivity, and the electrical conductivity is compared to that of a KCl solution held at 15 degrees Celsius. And the true formula for salinity based on its electrical conductivity is given over here. So I'm not going to go too much into the details of it. But remember one thing, in modern day, when somebody is reporting salinity, it has nothing to do with the measurement of the amount of dissolved salts in that particular parcel of seawater. They're essentially measuring conductivity, and from the conductivity data, they are converting it to salinity. Now, what is the impact of salinity on freezing point and density of seawater? Now, we all are aware of colligative properties. What are colligative properties? That the property of a solvent is different from in a solution than in a pure form. It's manifested in elevation of boiling point, depression of freezing point, changes in osmotic pressure. Now, what we have here is the salinity or the amount of salt content of the water going from 0 to 40 along x-axis, and the temperature going from around minus 2.5 to 4.5 along the y-axis. This dashed line gives you the freezing point of water of different salinity. This line gives you the temperature of maximum density for different water parcels of different salinity. Now, when you are at zero salinity, the freezing point is 0 degrees Celsius. This is essentially fresh water. So fresh water has a freezing point of 0 degrees Celsius and a temperature of maximum density of 4 degrees Celsius. What we need to note from this graph is that there is a depression of freezing point as you keep adding salt to it, and that there is a change in the temperature of maximum density as you keep adding salt to it. Now remember, the slope of the two lines are different. So the freezing point depression is a much shallower line than the change in density. So the effect of salinity on density versus the effect of salinity on freezing point are slightly different. Now, beyond a salinity of around, say, 24.7, there is no change in terms of the temperature of maximum density. The two lines have merged. That is reflected in this particular graph. What we are looking at here is temperature on the x-axis from minus 2 degrees Celsius to 34 degrees Celsius. In the top y-axis, we have the seawater in density given in grams per meter cube, going from 1022 to 1030. And in the bottom y-axis, we have fresh water going from 994 to 1000. The shape of the freshwater curve is what we expect, right? At 4 degrees Celsius, we have maximum density. On both sides, the density goes down. As the temperature goes up, density goes down. Below 4 degrees Celsius, also, density goes down. However, for seawater, the maximum density is reached at its freezing point, which is around minus 1.9 degrees Celsius. So for all practical purposes, minus 2 degrees Celsius. So the take-home message is that seawater, any seawater parcel for a salinity above 25 per mil doesn't undergo a density inversion with temperature. So its temperature of maximum density is right at its freezing point. Keep that in mind. Now, density of seawater can be expressed through this ridiculously complex equation. Okay, it's a function of its salinity, it's a function of its temperature, it's a function of its pressure. Simply put, as you increase the salt content, density goes up. As you lower the temperature, density goes up. Pressure, we have been taught that water is an incompressible liquid, but sorry to disappoint you, there is a small compressibility factor, and that has an impact on its density. So if anybody is interested in calculating the true density of a parcel of seawater, they can use this equation to get to that. Okay, this is known as the International Equation of State of Seawater, proposed in 1980s. But this takes us to a very important observation. What are we looking at? That these are the density equation. What we can see that there are density equations are not linear to each of the parameters. Okay. This diagram is known as a temperature salinity diagram. What we have here is salinity plotted along the x-axis and temperature plotted along the y-axis. And these contours belong to water masses of equal density. First thing to note that none of these lines are linear. They are curving, and the curvature is a function of this particular equation. However, when two water masses of the same density but different temperature and salinity mix, so we are mixing two water masses of the same density but different temperature and salinity, say point A and point B. Same density, very different temperature and salinity. Both temperature and salinity, or essentially the salt content, are conservative properties of seawater. You cannot change the temperature of a seawater without exchanging heat with another system, whether it's air or another water mass. So when you mix two water bodies of two different temperatures, the resultant temperature is going to be an average, or will be in proportion of the mass in which they are mixing. Same with salinity. So all mixing happens along a linear mixing line. This movement along this linear mixing line based on the proportion of each water mass will lead to formation of a water mass which is slightly more denser than the initial water masses. So when two water masses of the same density but different temperature and salinity mix with each other, the resulting water mass has a density higher than the starting two water masses. And in effect, when these two water masses mix, the mixture will sink and settle at a depth where it finds another water mass of its same density. So mixing of two water masses of the same density but different starting temperature and salinity will lead to formation of a more denser water mass which will sink. From that perspective, let's move to this particular diagram. We talked about this. As water moves from equator towards the pole, it's losing its heat, it's getting cooled, its density is growing up, and it's going to sink at the poles. So to put deep ocean circulation in terms of a heat flow diagram, this is what Stommel came up with in 1961. This is one of the first proponents of this system. At the equator, you have a hot system with high salinity. As the water surface moves towards the polar region, we have evaporation, which along the 30 degrees north, or from equator to 30 degrees north, whichever position you take, you will have evaporation. In some regions, you have precipitation. Some regions are netly evaporative. Your salinity will go up, and as you cool down, you're going to form deep water mass, which is going to flow along the bottom of the ocean, and then at some point it's going to get upwelled, and then again move back to the polar region along the surface of the ocean. So this is essentially the transfer of heat from the equator to the poles along the surface, and from the pole towards the equator along the bottom. As we move very cold water masses from the pole towards the equator along the bottom of the ocean, there is a net flow of heat from the equator towards the pole. And nothing explains this phenomenon better than the Gulf Stream, which is the movement of very warm water masses from equatorial Atlantic towards northern Atlantic. Essentially, this is the water mass which keeps the entirety of Europe habitable, Western Europe habitable. And you can see this water mass entering into the Gulf of Mexico, acquiring more and more heat, going through the Straits of Cuba, going along Florida, and moving towards North America and towards the northern side of America, and then crossing the Atlantic towards the Western Europe. In terms of deep ocean circulation, there are two places we can form the deep water masses. One is the North Atlantic, the other one is all around Pacific Ocean. Let's take North Atlantic. This is where we are looking at the global temperature. As expected, equator is heated up, polar regions are cool. This is where we are looking at the salinity system. As expected, we have some hotspots of high salinity around 30 degrees north and 30 degrees south. Equator doesn't demonstrate a very high salinity because whatever evaporation happens leads to precipitation in the same regional uh, range. So there is a net evaporation and precipitation cycle that's going on. However, the 30 degrees north and 30 degrees south belts are known as the net evaporative belt. So you can have high salinity in those regions. So these are pretty dense water masses. However, they're also pretty warm water masses. So though the salinity is increasing their density, the increase in temperature is also negating the salinity effect on density. Only when this water mass moves towards the pole, loses its heat, becomes far more dense, and thus sinks. So if we translate what we have in terms of salinity and temperature into a density, what we see that some of the densest surface water exists in North Atlantic and all along the Southern Ocean, that is around Antarctica. And this is the two regions where we have deep water formation. This is the North Atlantic deep water. This is the Antarctic bottom water formation. This is demonstrated in this figure. We have the movement of the warm water mass from the equator towards the pole. This is high temperature, high salinity water mass. But as it is moving towards the pole, it is losing its heat. It's becoming, but it's not losing any salt. There's not much net precipitation happening. So it's becoming more and more dense. By the time it's close to Greenland or Iceland, it's become so dense that it sinks, and then it follows the bottom of the ocean to come back to the South Atlantic. Along the Antarctica, the bottom water formation happens for a different reason. During the southern winter, there is large amount of sea ice formation. As sea ice forms, there is the salting out effect. The salt from the ice lattice is driven out. That mixes with the underlying water. So that water is already at a very low temperature, say it's at minus 2 degrees Celsius, and you're adding salt to it. So it's going to become far more dense and sink to the bottom. So Antarctic bottom water is dominantly formed under sea ice and has a higher salt content in a way due to salting out effect during sea ice formation. That takes us to a cross-sectional view of the Atlantic Ocean. What we are looking at is from 60 degrees south to around 75 degrees north in the Atlantic Ocean basin. This is a depth-dependent structure, and these are the potential temperatures. What we can see is the North Atlantic deep water formation here, formation of deep water of cold, dense water that is sinking to the bottom, and this is the Antarctic bottom water coming from the shelves, Antarctic shelves into the South Atlantic Ocean. The salinity also shows a very similar pattern. In terms of oxygen, what we can see that the oxygen concentration of the North Atlantic deep water in the high latitude is really high, whereas the Antarctic bottom water oxygen concentration is not that high. Why is that the case? Because when North Atlantic deep water formation happens, it happens while there is exchange with the atmosphere. Whereas when the Antarctic bottom water formation happens, there is a sheet of ice sitting on top of the seawater, so there is no net exchange with the atmosphere. And that is also reflected in the C14 data, because C14, as we know, is formed in the upper atmosphere and can only be exchanged with seawater when there is exchange with the atmosphere. So North Atlantic has a much younger age compared to the South Atlantic. So these are the evidences that we have, that these are the two places where we have dominant bottom water formation. And this bottom water circle, or the Great Oceanic Conveyor Belt, keeps happening, and it has a residence time of water in the deep ocean of around 1,000 years. Keep in mind, the residence time is 1,000 years. Okay. So in the next lecture, we're going to introduce the idea of residence time. We're going to look at how dissolved ions behave and how carbon dioxide enters seawater over time. Okay, do we have any questions for this lecture? Sorry.
Hello, sir.
Yeah, go ahead.
So actually, for the last 15 minutes or so, I personally had a lot of problem understanding because, I think your screen, it's lagging behind your voice.
Oh
So
dear.
say when you're at the Atlantic, your cursor is at the Pacific, and yeah, it's causing a little bit of difficulty for me to understand. I
Okay.
think it's happening for 4 or 5 of my friends as well, and might be
Okay.
happening for everyone, but I'm not sure. And I don't know if there's anything you can do about it really.
No,
But
it's
it might be,
essentially a function of speed at which we are, internet speed.
yeah.
Uh, did everybody had this problem, or is it specific to a few people?
So I don't know. At
Okay.
least 5 or 6 people did have it.
Okay.
Uh, and
So
yes.
if you have problem with it, just uh, drop me a note, and what I will do is I will repeat some of these things quickly. Do you want me to repeat some of it quickly?
Um, I don't know. Uh,
That's okay. You don't have to say yes or no right now. Go through the lecture notes, go through the TS sessions. If there is still some ambiguity, uh, drop me a line before the next class, and then I will start with a quick introduction to this.
okay, sir. Thank you.
Is that fair enough? Yeah,
Yes.
let's do it like that. Yeah. Any question or any ambiguity from today's lecture?
Also, sir, which is do you have any textbook like or something that you're following that you expect us to follow for this module of the course?
I'm trying to sort it out. I can give you the Habitable Planet textbook, which is kind of the gold standard for this sort of lectures. But this kind of a lecture is a mission mash of a lot of information from different sources. Because the way my predecessors had designed the syllabus is very difficult to stick to one textbook. What I will do is I will share the Habitable Planet with all of you, and just follow that. Okay, because that gives you an overview how the planet functions as a I wouldn't call it an entity, as the heat balance of the planet, and what are the feedbacks, effects, and everything.
Okay, sir. Thank you.
Yeah.
So I think it'll be beneficial if you drop like all the sources that you're using apart from the book too.
That is a difficult thing to do for me, because there's just too many sources. I'm sorry about that. Some are unpublished data, some are uh, just random downloads from the internet. So it's a bit of a hodgepodge. Yeah.
Also, sir, have you decided about the assessment for this module? Like, are we going to have an end-term exams or something of that sort?
That's a tricky question. I might go for an open book exam. I'll definitely go for an open book exam for all of you. Um, Mostly based on the kind of the numerical problems we're going to solve for this part of the module. There will be an emphasis on carbon dioxide dissolution in seawater, uh, the pH effect of carbon dioxide. You did some calculation on the solar constant, right?
Yeah.
My question to you is that did Professor Ghosh cover that in details, or was it done slightly
No, he
superficially?
didn't. He didn't.
You did.
It was just mentioned.
It was
Yeah.
just mentioned. So the kind of numerics that we can do based on the bits that I have covered, would you guys be comfortable with doing that?
Sure. I think it's fine.
Good. Uh, good.
So will the end semester exam be based only on your module?
Uh, I would say 70 to 80% will be based on my module. This is a conflict that I have to resolve with my colleague. Okay.
So it would be better if it's based on a single module, or
I'll
otherwise, if it's
I'll
based on the
try.
previous module, it would be great if you could, pinpoint that, say, the last 4 lectures would be included, because we had many lectures, and to go over all of those for the end sum again would be a difficulty for us, I feel.
I understand that. The unfortunate thing is I was supposed to start in November, and I got pushed back to December, and like 25th was a holiday. What is Friday? First, right?
Yeah,
Yeah,
it's
that's
first.
also,
Yeah.
yeah.
Should we take a class or should we drop it? Like, what will be the consensus?
The consensus would obviously be to have a holiday, but
Yeah,
That's
but
tricky.
we have other things happening on first. It's technically not a holiday.
Yeah.
I know.
Yeah, we have
technically,
exams as well.
Yeah. Okay. So I'll try and take a class on the first, okay, provided I am myself in a position to take a class, so we will sort it out. Yeah. Okay, but 99% we'll have a class on the first, okay, because I've missed just too many classes. Um,
So have
so
you decided on what will be the weightage for the assignments that we receive every week?
that also depends on how many can we complete, because after today's lecture, we won't have many numericals, right?
Yeah.
This is mostly a subjective kind of overview of what happens in the system.
Yeah.
But then from the next lecture onwards, we're going to get into the details of calculations, derivations, and stuff like that. So depending on how difficult it is, the first assignment maybe will have 5 marks or something like that. So I will have to take a judgment call on that, by how far we can go with the lectures.
Okay. Yeah.
And the final exam is going to be open book, so let's not worry about that. Any other question? Okay, docs. If you guys don't have a question, should we end here?
yep.
Thank you.
Thank you,
Bye-bye.
sir.
Bye. Bye.